Cool. All right, so let's begin with chapter 4. Finish with chapter 3. I'll try to go through these here, and if we're sort of behind a little bit, I'd rather give you guys a little extra time to ask any homework questions from chapter 3, because I know there was a lot of information. So if you need the extra time, I'll at least give it to you. Okay, so we're going to move on to something called multiplication of polynomials and the whole concept of polynomials. But before we even get to polynomials, we're going to go back and we're going to put in a whole bunch of information about exponents, exponent rules, because we need those when we get to polynomials. So what in the world is an exponent? Again, this is going all the way back to pre-algebra, just sort of connecting the exponent is this little extra little number on top right after the number itself. And so that guy is called the exponent. The big number here, that's called the base, and this number just tells you how many times we multiply this times itself, right? So 5 to the second power, or we say 5 squared sometimes, is we just mean 5 times 5. So 5 to the third power, or we say 5 cubed, it just means we're going to multiply 5 times itself 3 times. We're good? Some fun stuff here. Since we live in 3-dimensional space, we have this little name called squared for the second power. We have cubed for third power, but then after that we always just say 4th power, 5th power, 6th power. Nothing special after that because of the dimensions we live in. Alright, so with that, let's go for it. I got ABC, and then I put in some extra B. So I put a star B and a star C, just to give us a little bit of a difference there. Alright, what gets confusing here are parentheses. Parentheses are the confusing aspect here. Alright, so for A, so if you have 10 to the second, really means 10 times 10 or 100. With B, first of all, notice there's no parentheses. So if there's no parentheses, this 5 is only acting on the number in front. So it kind of looks like this. And if you want to fill in the information here, that's fine. There's a negative just sort of sitting out here. And then there are 5 2's multiplying themselves together. That's what it means. We'll get to this one here in just a bit here. So 2 times 2 times 2 times 2 times 2, that's 32, with the little negative just sort of hanging out in front. Okay, good there? Now, if you want to include the negative with the number itself, what you do is you put parentheses here. So in this case for C, and I think that's the one I'm going to do next, yeah, for this one, this means this. You're multiplying a negative 3 times itself 3 times. Good? So negative 3 times negative 3 times negative 3 gets you a negative 27. Okay, so let's switch it up a little bit. So this one, no parenthesis, just means one single negative hanging out in front. This one means that number itself is being multiplied times itself. Okay, so negative 2 to the 5th power, what does that mean? Negative 2 times negative 2 times negative 2, 5 times over. Cool. All right, in this case, notice that for star B, we get the same answer. So Mr. H, it doesn't really matter which way you go, one or the other. Well, actually it does. On certain occasions. It only really matters if you have an even power or an odd power. Because remember, an odd number of negatives multiplied together still give you negative. So it doesn't matter if it's negative in front or but star C, that's where the difference is. So if you have a negative 3 multiply itself to an even number, that's where the negative just sort of disappears. So negative times a negative times a negative times a negative is a positive, so then 3 times 3 times 3 times 3 is just going to be 81.
Okay, so if it's to a positive number, the exponent, then it's going to be a positive number. Like if it's a
The difference if it's an even or an odd exponent.
So
Okay, good, good. So odd will get you, and a negative even will make the negative disappear.
okay, cool.
And of course, there are something called fractions here. So I'll let you guys finish that one off. Cool. Most people almost done here. Alright, there's 3 of those being multiplied together. But again, a negative times a negative times a negative, or an odd number of negatives will still just give you a negative. You just have 1s on top, so just get a 1, but 5 times 5 times 5, how about 125 on the bottom? Okay, so again, just working with the whole concept of a definition of an exponent. Then let's jump to the rules now. And these rules you're gonna have to put on a 3x5 card. So property number 1. It just means if you are multiplying 2 expressions that have the same exact base, notice the base is always a. Instead of multiplying them all out completely, what we can do is we can just add the exponents up, and that'll give us the answer. So again, just an example from pre-algebra. If you have 7 to the 4th power, that's 4 7s multiplying together. The 7 to the 2nd power just means 2 7s multiplying together, but really, technically, aren't you really saying that there are 6 7s being multiplied together?
Yeah.
And so 7 to the 6th power, and then we say, you know what, if this is the answer, how do we get from here to here easily? Let's just add the 2 and the 4 together and be done. So I'll give you guys a few problems to practice.
Okay, so and when you said it just equals 7 to the 6th power, that's the answer?
Alright, so let's go for it here. 3 to the 2nd times 3 to the 4th. How about it's just 3 to the 6th? And we'll leave it there again, because that is the answer. It's a exponential form, but that's still the correct answer. Alright, tricky one. What'd you guys get for B?
8, 6.
Awesome. A to the 6th, because there's like a little 1 right over here. Whenever there's no exponent given, there's we assume it's a 1. So a to the 6th. And again, if you have 3 or 4 or 5 of the same exact bases, we're still going to add up all the exponents together. How about 4 to the 12th? Okay, again, we're going to load up all on these properties here. So the next one. And these properties build on each other sometimes. Like the next property here, it really builds off the previous property. What happens if you have a base to an exponent, and then you still want to take an exponent of that? So you sort of have nested exponents. Well, if that was the case, then the formula says we're just going to multiply the exponents together. But again, how does that come about? If, example from pre-algebra, if it's 5 to the 3rd, and we're going to square that still, doesn't this 2 just mean there's 2 of these guys? So there's 5 to the 3rd, 5 to the 3rd, but we already know what to do with this. If we're multiplying 2 of these, all we got to do is add the exponents to get a 6. So then the question is, how do I go from here to here rather quickly? Hey, it's just multiplying. Okay, good there? Alright, all yours. Alright, hopefully the first one you got 7 to the 10th, because the 2 and the 5 multiply together. How about b to the 36th? It's 9 times 4. Alright, next property. And this one now is kind of getting more into the algebra aspect of things here. So property number 3. What happens if you have two different types of numbers here and you're taking power of those? What this says is that this power goes to each and every single type of number. And again, at this point, can't use any pre-algebra rules anymore because we have to have variables in here. So 2 to the x taken to the third power. Technically, that just means there's 3 of these guys, right? But if there's 3 of the same exact type, isn't there? We can bunch up the 2's together, make 2 to the third. Bunch up the x's together. That's technically x cubed because there's 3 of them. They're just repeating themselves. And in this case, notice they do want to reduce this down to just an 8 or simplify it down to an 8. Okay, slightly more complicated problem, just for us to look at here. Again, this is more of algebra type here. So negative 1/4, x to the second, y to the third, and I'm going to have to square this. Well, that little square has to go to the number itself, and then to each of the different types of variables. Good there? So then negative 1/4 times a negative 1/4, negative times a negative is a positive, 1/4 times 1/4 is 1/16. That's cool. And then we got this little rule. Remember that? All we got to do is multiply these guys. So 2 times 2 is 4. 3 times 2 is 6 for the y variable. So notice these rules are sort of getting intermixed with each other. We just used rule number 3 the first time, and then we actually used rule number 2 to simplify. Alright, got a couple people, or a few people writing it down, so go for it. All right. So practice problems here, all yours. All right, I'm going to begin as well, at least for A. Just give us the answer, then you look up when you finish B. So 1/2 c to the third. Again, the 1/2 has to be taken to the second power, c to the third taken to the second power. So as you square 1/2, it becomes 1/4. And then multiply the 2 and the 3 together. How about c to the 6th? Good there? Love math. It's so logical. Just sometimes we're the ones that are not that logical. Okay, for this one, how about negative 2 taken to the third power? A to the 4th to the third power. Again, the x variable and the y variable. All right, negative 2 times negative 2 times negative 2, negative 8. In simplified form, and then how about a to the 12th? Good there. X to the 6th. And then remember, what's the little number right here that we don't see?
1.
1, so technically it's 1 times 3, so it's y to the third. Quick here, show of hands, somebody got that one before I gave the answer? 2, 3, 4, 5, 6. Okay, cool. More than half, that's good. Okay, now let's really start mixing things together. Okay, let's see how we can mix these different rules up. All right, I'm going to go for it here. So these rules sort of get mixed up here. You got to figure out which one you want to use first here. In this case, it's going to be the product of product rule here. So it's going to be the multiplication of the exponents. At that point, once that is done, then you say, hey, you know what? To have the same base, I'm multiplying these guys together, I can still add together. So x to the 36th. This one, again, just a little more complicated here. That means, and you can skip a few steps if you like. You can probably do this in, we could probably do this in our head here. 3 to the 4th is going to be 3 times 4. 8, and how about z to the 4th? Everybody okay with 64? Now notice with the number itself, I do have to put in parentheses, just to understand that it is multiplication, right? Okay, how about x to the 15th? Because it's 5 times 3. Y to the 3rd, it's 1 times 3. Z to the 6th, because 2 times 3. Alright, the number itself, the base, or the coefficient here, what we do is we always bring out the number in front. We don't like numbers in the back of variables. We usually bring that in front. And then this one looks like it's all multiplication, therefore we're going to just be adding the exponents here. So how about x to the 27th, y to the 11th, and how about z to the 10th? Okay, and again, show of hands, how many got that one right before I gave the answer? Ooh, a little bit less this time. Okay.
I thought y was 24. This isn't it.
All right, so let's take a little bit of a detour here with this, with these different exponent rules. Look at just a quick application to these things here. So scientific notation is application of these rules of writing with exponents. I don't want to say this here. Let's see. In astronomy, sometimes we have very, very big numbers here. Sometimes in science we have very, very tiny numbers. And we don't want to put all the zeros when we don't need to. I want to write this in most condensed form possible. And so in science particularly, we invented a way to write this simply in scientific notation. And it looks like this. And the funny part, see this little x right here? We sometimes use that little letter x in algebra, right? Because it's right there. But anyways, n has to be a number between 1 and 10. Notice you got this little less than or equal to and less than symbol. N could be 1, but then it can't be 10. So 9.999 would work. Good. 9.9999999 would still work, just not 10. A little easier way to sort of see it is that we have one digit in front of the decimal place. Like if you think about it, like 5.7, that's a number between 1 and 10, right? 8.3, that's still a number. If I say 12.3, no more, right? Because it just needs to be just one digit in front of the decimal place. Okay, then we write times. This is the pre-algebra. Remember, this is the pre-algebra symbol for times. And it's 10 to the r. R always has to be an integer. So, like a number like this, let's see, this is thousands, a thousands place, millions, billions, now we're in trillions. So 5.88 trillion. That's kind of how we want to say it, right? So if we say 5.88 trillion, that's kind of what scientific notation is all about. So if I want to change this up, it would be times 10, and then all I got to figure out is how many multiplications of 10 are here. And the way we do it, remember, because multiplying by 10 all just moves the decimal place once, right? So if we think about it, we just have to count the decimal places here. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So that number written in a little bit more condensed form would be 5.88 times 10 to the 12th. Alright, what is this? Anyways, this is called a light year. This is how fast light travels given a whole year's worth of time. Not bad, huh? Okay, the fun part about it is it takes 4.3 years traveling at this speed right here to get to the closest star, to get to the next closest star in our galaxy. Isn't that kind of weird? So times that by 4.3, and that's how many miles we are away from the next closest sun, in a sense. Do some other weird stuff. Can I tell you some other weird stuff from science? You guys ready? How do I say it? Einstein. When Einstein was talking about light year, what he figured out is that light actually controls time. So when we look at an object, actually it takes light to go from one object to another. Is that kind of weird? So he said if we're on one planet over here and we're on another planet over here, and it takes, and this is exactly 5.88 trillion miles away. Good. So if I was walking, Mr. Stickman, and I fell down, we're good? And another person was here looking at me from this planet, and he had a telescope that can like see me, right? It would take him a whole year for him to see me that I fell. Good? Because the light, since Einstein says light controls time, the light had to travel all the way here. So what happens is this person here is actually seeing, if he's looking at the Earth, he's seeing what's happening on Earth a year ago. Cool? Kind of
Even though he
weird.
just seen it?
Even if he's just seen it, he's like, oh wow, that's
It
what
was
happened a year ago.
Oh, okay.
So that's how weird time is in outer space. So, since we're closer to each other here, right? So technically, Einstein, since Einstein is correct, and we've proved it over and over again with other experience, I actually don't see you, you guys don't see me. We see each other like a split of a second later. Does that make sense? Because it takes the light from your eyes to get to the light on my eyes, and then I see you, and so there's a little bit of a time gap between us and any two
So that
objects.
movie Interstellar could be true.
Ooh, haven't watched it yet, but
Oh,
that
you haven't?
no, okay.
Instead, watch it once.
Okay. Once, okay.
I had to watch it again, but it's fine. Matthew McConaughey's in it, so.
Okay, we'll get there. I thought it was kind of an interesting little concept there. Oh, one more thing. Ready for this then? So, it takes the light of the sun, because technically our light is on this, can't say a galaxy, what is it? Solar system. The light in this solar system is controlled by the sun, correct? And so if the sun were to blow up, it'll still take some time for us to understand or know that it blew up. So we won't know that the sun blew up until about 5 minutes and 20 seconds later, because it takes the light from the sun to reach us that long. So whenever you're looking at the sun, we're technically 5 minutes and 20 seconds late than what's happening up there. So interesting how time and space works. It's okay. Anyways, back to math here. You can't have fun here. You can't be talking about good stuff like that. Okay, so 1.637 million looks like, right? Can you transform that into scientific notation? Cool. Go for it. All right, just a little aside here. On the notes, when you're doing these exponent rules, sometimes what the book will do, the book will actually put in a 1 for the exponent, and sometimes it won't. It's just sort of getting you guys used to that there's sometimes a 1 there. Initially it starts doing it, and then it just sort of drops it off, just for you guys to understand there's a 1 there, even if you don't see it. That's for the exponent stuff. But scientific notation, here it is. So what I usually like to do, I look at this number and say, okay, where should the decimal be? If this is a number between 1 and 10, the decimal should be right there. Is that right? So my number should be 1.637. Of course, you got the little x from pre-algebra, you got the little 10, and then we start counting the number of decimals. 1, 2, 3, 4, 5, 6 looks like. So there's my 6. All right, it starts dealing with only large numbers now. Later on we'll deal with the small numbers because they work a little different. Okay, and how about the other way? 9.36 times 10 to the 5th, what actually is that?
It's already in
It is inside of notation because now can you put it into expanded form? So going back the other way here. So the way we do that, we just write down 9.36 the way it is, and we're going to start us counting off the decimal places here. So 1, 2, 3, 4, 5. Leave a dip in each one of those here. We're going to fill in the rest of the dips with zeros. All right, what number is that? Yep, 936,000. Well, that works. So we got a comma between the 6 and the 0. All right, so there's the rules there. Keep on going here. Now instead of multiplication with exponents, now we're going to change gears a little bit here. We're going to talk about division. What about division? What happens with dividing and exponents? And the first definition we come across is this whole concept of the negative exponent. And these ABC, that is not from the matched problems. This is just an examples for us to look at. And again, coming from pre-algebra here. So if you see a negative exponent, what that technically means is, I think we know it as reciprocal. So if you see a to the negative r, we take the reciprocal of a, which is 1 over a. And notice the sign on the r changes. You can think of it this way, or you can also think of it as a fraction. All right, and okay, really, this is a little pet peeve of mine here. This kind of is sort of backwards here. Let me show you what I mean here. Whenever you have a to the negative r, let me do it this way here. Again, it's the same exact formula, but it makes more sense if we think about it this way here. So tell me, what is the reciprocal of a?
1 over 8.
1 over a, right? Reciprocal of 5 is 1 over 5. Reciprocal of 7. So if I take the reciprocal of a, what I should have is 1 over a to the r, right? Because notice a, now it's the reciprocal of a, and what I've done is I changed the sign on the r. Now the question is, what is 1 taken to any power whatsoever? So 1 times 1 times 1 times 1 times 1, still 1, right? So that's why the r does not affect the 1 whatsoever. The top is still going to be a 1 no matter what, but the a is affected by the r over here, so it's a to the r. We good there? That's how we usually think of it this form, but it really comes from this whole concept of multiplying 1 times itself doesn't change the 1. Okay, so real quick here. How do we do this here? Some examples from pre-algebra. 2 to the negative 3. What we do is we take the 2 down to the denominator. We change the sign on the exponent, and then we simplify if we can or if we need to. Same thing happens with 5. 5 to the negative 2. Take it to the bottom. If it is already in the denominator, we're going to bring it up to the numerator. So we'll see some of those as well. Alright, and C, the one that students get mixed up on. Notice there's no parentheses around the 3 and the x. If there are no parentheses, that negative 6 is only acting on the x only. Cool there? 3 separated from the x. 3 stays wherever it wants to stay, but the x has to be the one that is going to the denominator. And then simplifying over, 3 on top, x to the 6th on the bottom. Okay, so practice problem for you guys. All yours. So I got A, B, C, and of course a star C. So 5 to the negative third power means 1 over 5, and the 3 is on the bottom. At that point, then taking it to the third power is 125. B, 10 to the negative second, which means 1 over 10.
What about the negative?
Oh, what about the negative? Who said that? Korea, go ahead.
What about the negative?
The negative 3 here? Yep, changes into positive 3 because we've made this 5 go into the denominator.
So then
Initially, it was like this. It's in the numerator.
So then if it's a positive, it would be a negative at the bottom? If they
Correct.
was-
Yep. As soon as you switch the numerator denominator of them, the exponent has to switch signs. Cool. All right. 4, z to the negative 5. Again, the z and the 4 not connected to each other. 4 stays on top. The z goes down to the bottom with a positive 5. Okay, if you do want to connect them, there's a little one at the end there. Now connected, now that, because they're in parentheses, now the 4z has to go down to the bottom. And all that has to be taken to the 5th power.
It stays in parentheses.
Stays in parentheses still because they're not disconnected yet. But then I got to simplify. So how about I take the 4 to the 5th power now? And z to the 5th power. And so 4 to the 5th power, gotta think about it here. Sorry, I didn't give you much room there, but 4 times 4 is 16. Times another 4 would be 64. Let's do it off to the side here if need be. So 4 times 4, 16. 16 times 4 is a 64. Anybody know what is 64 times 4?
376.
Close. I'm gonna go with 2 something. 250, okay. 256, and then that times multiplied by 4. So eventually that will give you the, oh sorry, the 1024. Okay, good there. So it's 4 multiplied itself 5 times. Gets you 1024. And z to the 5th. Alright, any questions on that? I got a few blank stares here looking at the screen.
Okay, so then it becomes 4 over z to the 5th power, and then you just do 4 to the 5th power too?
Mm-hmm. So in this
Oh,
case,
okay.
this breaks down into 4 to the 5th, z to the 5th, and then you simplify that to get you 1024.
Oh, okay.
Alright, so that's the reciprocal, or sometimes called the negative exponent rule. I got some more for you. Property 4. Alright, and the book actually does not explain where it comes from. That's not cool. Okay, so let's do this here. Let's go with x to the 9th divided by x to the 6th. I'm going to explain A, where this rule comes from here. If you have x to the 9th divided by x to the 5th, doesn't that mean that you have 9 x's here, right? 1, 2, 3, 4, 5, 6, 7, 8, 9. X to the 6th means you got 1, 2, 3, 4, 5, 6. That good? But we also know from fractions here, if you have the same exact number on top, same exact number on the bottom, these will cancel each other out each time, right? So if that's the case, each of the x's cancel, 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 and what am I left with? I'm just left with x to the 3rd. Good there? So again, this whole concept of the relationship. How do you go from x to the 9th divided by x to the 6th, and I get x to the 3rd? Well, easily we just subtract. Okay, so for A, again, 9 subtract 6 is the easiest way to do it. You get x to the 3rd. Sometimes when you subtract, you actually are going to have a negative exponent. And if you have a negative exponent, then you do what we just learned negative powers, you gotta take it down to the denominator. Alright, how about, and if there's just numbers, no variables here, x to the 15th, I'm sorry, 2 to the 15th, divide 2 to the 20th, subtract that, you get x to the negative 5th. Have to take it down to the denominator and simplify as much as you can. Everybody okay with 1/32? So again, lots of rules here. There's one rule here, two, and then simplifying. Okay, let you guys get started. All yours. Give you a minute or so. All right, we'll get started here. So it looks like it's going to be 2 subtract 3. Do this here, but when you do get that, you get x to the negative 1, and a little extra little thing here. Because you got the negative exponent, y goes to the denominator, but you really don't need to put a 1 here, right? Remember? Because we assume if there's no number there, then it's a 1. So always the question is, Mr. H, how about if I put a 1? Is that still okay? That's still okay. You could put a 1 there, but if you don't put anything, that's good as well. Cool. B. A to the 6 subtract 2, that's pretty straightforward. A to the 4th is the final answer. Keep it like that and everything's good. This one, it's going to be 8 subtract 12, which makes 3 to the negative 4. And again, can't leave exponents as negatives. We've got to take that 3 down to the denominator. At this point, we can simplify that here. 3 times 3 times 3 times 3. 81. Cool. All right, another rule. Sheesh. Rule 5. What if you have 2 different types of numbers here? Alright, the reason why I put a little proof here as opposed to an explanation here, because when you get up to higher mathematics, this is what we do really after calculus. After calculus, it's kind of interesting if we think about it. We have this algebra class here. We move on to intermediate algebra, which is Math 63. Then there's some geometry sprinkled in there somewhere, right? But then you move on to trigonometry. Then from trigonometry, you move on to calculus. And calculus, there's so much there, it takes about 3 semesters to get through calculus. But after you do that, we are pretty much done as far as computational mathematics. And as you do math up until calculus, you see how everything sort of fits together. Geometry tends to all make sense. Algebra is sort of almost like this pyramid that leads up to the top. It's usually second semester calculus where you're like, oh wow, that's what I've been doing all this time. That's why we did that in algebra. That's why I did that in geometry. Because everything finally culminates in this one semester. And you're like, I see the peak of the mountain. This is so cool. And so after that, then there's really no, I mean, statistics is sort of like on it's an application really of, but formal mathematics. So then after that, really it's just this stuff right here. It's just all proofs. It's all theoretical mathematics after that. And so you proof stuff that can be or can't be and all that good stuff. So that's what it looks like. So after calculus, notice you don't see any numbers anymore. You just see letters and letters and letters. The only numbers you see are the page numbers in the textbook. That's about it. Kind of weird. Okay, but it doesn't explain this already, so let's take a look at how to explain this, and I'm going to just kind of draw it out maybe like right here. So if I say this, if I say 2/3 taken to the 4th power, that technically means, right, you got 2/3 times another 2/3 times another 2/3, another 2/3. But eventually, if we think about it, aren't you just multiplying 2 times itself 4 times? And aren't you multiplying really 3 times itself 4 times? So you see, you know, that exponent of 4, or that exponent of r, really just goes to each one of those numbers. It goes to the numerator, it goes to the denominator. And again, simplified version, I don't need to keep on rewriting that same exact number so many times. Okay, so let's go with this one here. Some example problems here, just for us to think about. So x over 2 to the third power, that means that 3 goes to the x, 3 goes also to the 2, and if we can simplify it, go ahead. So there's your x to the third over 8. How about 5 over y to the second? Again, in this case, the 2 goes to the 5, the 2 goes to the y as well, but then you simplify the top only. Alright, and it goes, hey, there's a 2/3 to the 4th. I got it. Okay, so instead of doing that, I could just say 2 to the 4th, 3 to the 4th, and then I simplify this by itself, simplify this by itself, and done. Okay, good there? Alright. All yours. Alright, I'm going to go for it here. So for the first one here, I have a d squared over 3 to the second, and I can simplify that down a little more, just to a 9 here. So how about d squared over 9? The other part here, to the 5th, how about z to the 5th, and then simplifying the top, 2 times 2 times 2 times 2 times 2, 32. And z to the 5th, and again for c, that 3 goes to the 2, the 3 also goes to the 5, and at that point then we are simplifying each of those here. So 2 times 2 times 2 is 8, 5 times 5 times 5 would be 125. Okay, and the other part we got to think about here is this whole concept of 0 and 1 as an exponent. So by definition, or just the way we do things here, if there's nothing here, really technically there's always a 1. So it's just trying to say those two are the same thing here. If we were to cancel each of these like we did earlier here, we would be left with just an x by itself. If we did the rule here, 3 minus 2, we would be left with x to the 1. And since these two are the exact same problem, that means these two are also the exact same thing. Okay, good there? This one here, and now the whole concept of 0. What does it mean to be a exponent of 0? Cool. 5 to the second, 5 to the second. If these two are this exact same number, if I simplify them, 25 divided by 25, wouldn't that be just a 1? But over here, if I do the exponent rules, I would have to do 2 subtract 2. If I do 2 subtract 2, I get 5 to the 0. Hey, that means these are the same. Good there? So that means any number to the 0 power would be 1. Good there? The only one that does not work, and the book just sort of briefly mentions it, guess we should put a little more consideration on it, is this whole concept of this does not work. I put a little, sorry, that should be equal to with the slash through it. There's no such thing as 0 to the 0 power. Because if I have a base that's 0, can I do this ever? Is that possible? Yeah, can't divide by 0, right? There's no such way. So we have this little rule that says a to the 0 power is 1 as long as a itself is not 0. But you'll never see that in math anyways. You're never going to be a 0 to the 0 power. It's not going to happen.
So we're not going to be quizzed on it?
No, no quiz on that. Okay, but I did want to jump to this right here, which I believe inside your textbook. Let me find the page number here. Page 250. And that's the one that, nice page number here. That one has sort of like a review of all this stuff. It has the 5 different properties, and then it has the 3 definitions. So again, the negative exponent, the 1 exponent, the 0 exponent, and these 5 properties here.
Should we write this down?
We've been writing it down all along, so that's fine. Okay, so here's what we're going to do. For the rest of the section here, we're going to sort of jumble everything up, and we're going to just start simplifying as much as we can. Okay, start off pretty easy here. We'll work our way to more difficult ones here. So all yours for number 4. Right here. So 3 to the 0 power is? 1. Perfect. Okay, by definition. Yep, 3 to the 1 power?
3.
Just 3. Okay, and then some addition here. 5 to the 0 would just be a 1. 3 to the 1, we just said it was 3, so then the final result is a 4, because we're going to have to add that up. Alright, so 6d squared r, all that taken to the 0 power is?
1.
Just a 1. Can't trick you guys, you're too cool. Okay. Alright, then how about this one then? Again, try it yourself first, and we'll look at the simplified version here. Alright, I'm going to start here as well. So usually what we do is we try to get rid of the parentheses first, because once you got parentheses, then you got individual pieces, and then you can sort of work with individual pieces here. So at this point, got the little 3 here. What's 3 to the 4th power going to be? 81 is good. Yep, 81. And then y to the 2nd to the 4th? Y to the 8th. Notice on the denominator, nothing to be simplified at all whatsoever there. So just keep it exactly the same. And then I got a y on top, I got a y on the bottom, or I got a y in the numerator and the y in the denominator, so let's subtract them. So how about 8 minus 9 would give you a negative 1.
Can you just write like negative y instead of writing the negative 1 on the top, or would that mean something different?
Question is, can you write a negative y?
Yeah.
Yeah, no, can't do that.
No.
Because the y itself is whatever number it is. It's the exponent that's going to be the negative. Good there? So the y stays the same, no changes to the y whatsoever. Alright, still can't have negative exponents, so what's going to happen to this y? Has to go to the denominator here, so 81 still stays on top, remember, they're not connected. But then the y goes down to the bottom, 81 over y. Ha! Raise your hand if you got all that correct before I give you the answer. Ooh, 2. Okay. It's okay, we'll work with these here. Okay, next problem, something somewhat similar. It's all yours for this one. Alright, so let's go for it again, getting rid of the parenthesis first. So u to the negative 6 on top, u to the positive 6 on the bottom. So I got these two. Okay, kind of careful here. There's going to be subtraction between the two, right? So it's going to be negative 6 subtract 6. Ooh, not 0. Negative 6 subtract 6. Got myself a negative 12, is that right? Alright, question will come up, Mr. H. How did you get that? Remember with this one, negative 6 subtract 6, which means I'm going to put a plus sign here, take the opposite, and there's my negative 12. Okay, can't have a negative exponent. So the u has to go to the bottom. That means only there's a 1 left on top. And how about that? We good there? Okay, I want to show you also that these exponent rules, you don't actually have to follow one particular pattern. You can go to get to the answer in a different way as well. And this is a pretty good illustration here. And so notice if we start off with u to the negative 6, u to the 6. What happens with this u to the negative 6? Could I take this down to my denominator? Is that okay to do? Because negative, I'll bring it down to the bottom. That would make a positive 6. Good there. So it looks like this. 1 stays on top. U to the 6, that's this one here. But this one has to go down to the denominator so that my exponents are positive. We're good there? So notice now they're multiplying each other. So if they're multiplying each other, all I got to do is add the exponents. And notice you still get the same answer any which way, or any of the exponent rules you choose to use. You're going to get to that answer as long as you keep on simplifying. Okay, good there? Alright, again, next one. Let's go a little bit more difficult. Let's try it first, then we'll look at it together. Alright, since I see most people done or finishing up here, so let's go for it here. So I'm gonna put every single step in here, but you guys could have just skipped a few steps here, that's okay. So on top you should have L to the 9th power. On the bottom, 2 to the 3rd. And then that goes down to W squared to the 3rd still. I can simplify that. So again, L to the 9th. 2 times 2 times 2 is 8. And then have a W to the 6th at the end of it all. Good there. Okay, next one. A little bit easier. Alright, going on with this here. So the 2 here is completely on the outside, is not affected by this whatsoever. The -3 is only affecting the k to the 8th. So how about k to the -24th? And again, can have negative exponents. And the k is still not connected to the 2, so how about a 2 being on top and k to the 24th on the bottom? Alright, next one. Alright, if you have not found out yet, this is a little bit of a tricky one here, because -2 plus 2, that would give you a x to the 0 power, and with that, then it'll just be a good old 1.
You can't just leave x.
Can't leave it as x to the... If you leave it as just x, that means it's x to the 1 power, and it's not. And then you can't leave it as x to the 0, because any number to the 0 power still simplifies to 1. Alright, let's get really, really crazy now. I'll let you guys try this one here. Can you go from beginning to end? Alright, let me start it here. I'm going to give you just the answers here. Ask me if you have any questions on it here. On the bottom should be a q to the -21. And then, kind of depends which way you want to go. You can make all the exponents positive by moving things around, if you like. You can just keep on doing simplifying. So 10 plus a -7 on top will give you a 3. Again, this is probably more work with negatives than there are with the exponent rules themselves here. At this point, then you're looking at a q on top, q on the bottom, so I'm going to be subtracting, but in this case you're going to do is 3 subtract a -21, or you could bring that q to the -21 up to the top, and that means you're going to be adding. So how about q to the 24 at the end of it all? Alright, real quick here, show of hands. Somebody got that one correct before I gave the answer? Not cool, okay. I'm going to give you one just to sort of practice on. I know that was a little bit of a tough one here. So an extra little problem. Again, this is coming from my head. So, or maybe a homework question. Okay, it came from the textbook. Alright, again, try it yourself. Alright, I'm going to go with it here and simplifying. And again, you could have done it slightly different from mine, and that's okay, as long as you still wind up with the same answer here. So a to the +15 as you multiply -5, -3, a to the -7, and then a to the -15 on the bottom. And if that's the case, I'm going to simplify the top here. So 15 plus a -7 makes a to the 8th. Okay, and then at this point you could subtract, or I just like to move the a to the top. So I'll put a to the 8th times a to the 15th. Everything moved up to the numerator. And at that point we add them up and you get a to the 23rd. Okay, show of hands, how many got that one correct before I gave the answer? Cool, okay, a lot better than 0. All right, and then just some application questions just real quickly here. Number 11, number 12 has to do with this whole concept of variables, looking at variables, what do they mean, and at the same time dividing variables with variables. So one square is larger than another. If the side of the larger square is 5 times as long as the side of the smaller square, so how many of the smaller squares would fit inside the larger square? So I guess we're dealing with squares, so let's draw ourselves 2 squares, one being small, one being large. And since we don't know the length of it, we're going to have to just say x. So that's the small square. If I have a large square over here, we could actually even look at the area. What's the area of this guy? Close. How about x to the 2nd power, right? Remember with square, it's always the length squared, or width, length times width, right? X times x is x squared. Alright, then we have a larger square, and it says that if the side of the larger square is 5 times as long, well, we don't know what the smaller square is. We know that's x, so that means this guy would have to be 5x. So the length itself is 5 times bigger. Cool. Alright, I can always put 5x over here because we know it's a square. So whenever you say how many smaller squares, what you really are talking about, you're talking about area right away. And so we're going to get the area of this one right here. So this one's going to be 5x being squared. And gives us 25x squared. There it is. And so it says how many of the smaller squares would fit into the larger square. And if you think about smaller to larger, really what we should think about is division. You're saying how many smaller pieces would divide the bigger piece. So in this case it would be the biggest piece divided by the smallest piece. So what's going to happen to those x squareds? They cancel off, yeah, or you can say 2 subtract 2 is a 0, right? So x to the 0 is just a 1, but technically they'll just drop off. And so if that is the case, if one side of a square is 5 times as big, that means 25 of these small ones would fit eventually in here. Alright, let's go to 3 dimensions. That was a square. If we go to 3 dimensions, then we're going to look at a cube. And the match problems, they're actually wrong. They got 2 things confused here. So if you have number 12 for the match problems, just going to scratch out the first A and put a little B there. And the first B, scratch it out, put a little A. So it says if the side of a cube B is 5 times the side of cube A. So they got it a little bit wrong. Have to correct the publisher again. Alright, so the question is, we have to draw cubes this time. How do you draw a cube? I like it. Look at this here. What we usually do, that's cube A and that's cube B. Just label them like that. How do you draw a cube? You put a little square in front. Then you put sort of like slightly off, you put another square in the back. So it's sort of one is inside the other, but off slightly skewed. And then what you do is you connect each of the corners here. So corner on top, corner on the bottom, corner on the side, and corner on the outside. Oh, cool. Love it. There's my little cube. I know the... Okay, you guys get the big cube. Can you guys draw the big cube like that too? Okay, 2 squares, and then connect each of the pieces there. That gets you the cube. Alright, let's see. If the side of cube B is 5 times the side of cube A, so I guess I'm going to label one of the sides of cube A as just x. That means cube B would have to be 5x. So now the question is, how many of the small cubes would fit into the large cube? Any guesses?
I got 5.
5, okay. Let's go for it. So volume now, right? Because we're looking at volume now. We're looking at a cube piece. Okay, how do volume? Volume is the side, and what we do is we just cube it, whatever the side is. Because remember, with a previous problem, right? When we were doing squares, right? One of the sides was 5 times as much, and we were able to fit 25 of the smaller pieces into larger piece. Now that we have a 3-dimensional object, let's see what happens here. So the volume of cube A is just x to the 3rd. What's the volume of cube B? There you go, 125 x cubed. So then again, how many of the smaller will divide into the larger? So we take the larger bit divided by the smaller bit. Ooh, kind of cool there. All right. How about this? How about 125? The smaller cubes would fit into just one of those larger cubes if we extend the side by 5. All right, good there. So then, if you have extra time this week and have nothing else to do, I can give you a little trivia question here. So, here's our little planet right here. Here's the sun. And it takes how many Earths just to go around the diameter of the sun? Anybody know? This is how tiny our planet is. How about this? It takes 100 Earths just to sort of span the diameter of the sun. So, trivia question for the weekend here. How about how many then Earths would fit into one full sun? If you're talking about 3-dimension stuff. Yeah, we'll see. Another kind of fun stuff with the numbers here is, you know how we deal with big numbers and we sort of think like, okay, what does this really mean, right? So if you're talking about like the number 1 billion, what does the number 1 billion sort of feel like, right? Or what does it look like? So 1 billion. 1 billion is, it's like this. If you took quarters and you stacked them a foot high, right? Foot high, about, right? And you spread them all over the state of Texas. And you marked one of them with a little red X on it. That would be 1 billion. Or 1/1,000,000th of something. That kind of weird, huh? Look at the size of Texas, you're going to pick up one of them. That's huge. Just by seeing that. Okay, anyways. None of this fun stuff. We got to keep on going. Alright, more scientific notation. Like we have not had enough. I'm going to try to get it before break here. So, we already know this here. We know scientific notation is n times 10 to the r. But this time we're going to deal with very small numbers since we have the negative exponent rule now here. So an example here, 5.7 times 10 to the negative 4. If we hold true here, instead of multiplying by 10, what we really now are doing is we're multiplying by 1 over 10 to the 4th. So instead of really technically moving the decimal over to the right 4 places, what we're going to be doing now is we're going to be moving, or dividing by 10,000, or moving it to the left 4 places. So take this 5.7, and what we do is we're going to move this 1, 2, 3, 4. Put the little dot here. Fill in all this with zeros, and then what we do is put a 0 in front of the decimal. Not that you have to, but you can. So with negative exponents, we start shifting over to the left as opposed to the right. Numbers are really small. And I'm not sure if this is on your notes or not. I don't think so. This is, you sort of have to add in a little bit here. So just got 4 problems real quick here to finish that us off. So like I said, write each of the following numbers in scientific notation, and we're going to kind of go backwards here. Write each of the following numbers in expanded form. So we're going to give you this number, this number. Oh, we'll do those first. So can you give that to me in scientific notation? Alright, and again, the way I would approach it is trying to figure, okay, where should the decimal be? If this should be a number between 1 and 10. Yeah, 7.6, between the 7 and the 6, so that means it should have been here. So times 10, and then we've got to figure out where should it go. So I'm going to start out with this, where the decimal should be, and then where the decimal is. So 1, 2, 3, 4, 5, 6. So I had to go to the left 6 units in order to get to the end of the number. Alright, with a number that has just a single non-digit 0, what we do is we just write 8 by itself. We don't have to put 8 point. Now in science, depending on how much exactness you want with the number, you might have to do that, but the decimal then would be about right here. Starting where the decimal should be, ending where the decimal is already. So 1, 2, 3, 4, 5, 6, 7 would then be -7. Write the following numbers in expanded form, so let me change it up on you here. So how about these 2 problems here? And can you finish off those 2? Again, putting the decimal where it should be, which is past the 9, and then going back 5 spaces. 1, 2, 3, 4, 5. That is my new decimal point. Filling in the rest with zeros, and how about a 0.00009? Alright, the little trick to this last column here, if you saw it, Since you only have one single number in front of the decimal all the time in scientific notation, if you start moving this number this way, you're always going to get the exact same number of zeros as the number here. Does that make sense? Because you're going to move this 5 times. If you put a 0 in front of the decimal, then you're going to have 5 zeros here. So 4.56, you're going to move it 7 times over. And again, that means you're going to have really 7 zeros to finish it off. Alright, let's stop here.